Okay, we have here today another interesting integral from the UNSW CPMS Integration B 2023. This was finals problem 1. We have the integral from minus pi over 2 to pi over 2 cosine x over 1 plus e to the 1 over x dx. Okay, and I did a problem really similar to this not too far back, just a couple weeks ago, I think. And a few things are jumping out. Now, cosine x is an even function, 1 over x is an odd function, and we have these symmetric bounds. What I think will work nice if we do a substitution, we'll do our substitution u equal minus x. Because what that's going to do is flip these bounds around, and then we'll have x is minus u. We'll take our derivative and we find dx is minus du. So we'll go ahead with this substitution. Plugging pi over 2 in here, we end up with minus pi over 2 for the upper bound, and the lower bound becomes pi over 2. Again, just flipping that really. We'll have cosine minus u in the numerator, and then we'll have e to the 1 over minus u, but I'll write it as e to the minus 1 over u. And then we'll have this minus du here. But I'll take this minus sign I'm going to use to flip the bounds. So we'll take this out front here and I'll just swap these. And now our bounds are the same as they were in the original. But again, because cosine's an even function, we have a minus sign in here. I can just change that into a plus or make it go away. And now at this point, you kind of notice the similarity to the original integral. I want to get it so we have the same denominator and the same bounds. So what I want to do here is multiply by 1. I'll multiply it by e to the 1 over u over e 1 over u. And then we'll just distribute this in here. So for the numerator, we're just going to have cosine u e 1 over u. Multiplying this term with this term, the exponent becomes 0, and that's just going to give me a 1. Then multiplying e to the 1 over u times 1 just gives me e 1 over u. And now we almost have the same denominator here and here, but one thing I want to do is a variable change so that we can add these two together. So I'm going to change this variable back, and because it's a definite integral, I can change the variable back, so I'm going to change my variable from u to x. Okay, now I have this set up perfectly where the denominator is the same, and both these, we're using the same variable, same bounds. So what I'm going to do is I'm going to label my original integral as I. I'll label this integral also as I. We'll add these two together, and this is going to give me 2 copies, so that we'll call this 2i. Okay, so now with the rewrite, just notice we added this numerator and this numerator to get our new numerator over here. But now because we have cosine x in both these terms, we can actually factor that out. I can factor this as cosine x times 1 plus e 1 over x. We'll just copy over this denominator here, so we'll have our 1 plus e 1 over x here. But then at this point we get cancellation, so this is going to cancel with this, and now we're just integrating cosine of x. But one more thing before I integrate this, cosine x is an even function, and our bounds are symmetric around 0, so I can use the property that allows me to change the lower bound to 0, and then just bring a 2 out front. Sorry, I know we're kind of crowded right there. So I have this 2 out front of the integral, but we're also dealing with 2 copies of the integral, this 2i. So let's just divide by 2 on both sides. So now we've isolated I, which is just the value we're trying to find here of our original integral. And now we're just integrating cosine x. So we integrate that, and we just need to evaluate sine x from 0 to pi over 2. Sine x at pi over 2 is just 1. Sine x at 0 is minus 0. And so for our final solution, we just have 1. And now just to recap this really quick, again, in the original problem, we have here an even function in the numerator. We have some number raised to an odd function. We have a 1 right here, and we have symmetric bounds. So whenever you have an integral of this form, basically everything goes away and simplifies, and we're just left with this even function that's in the numerator, and we're left with that as the whole integral. The lower bound becomes 0, and hopefully this even function is easy to integrate like it is here, and then we can finish it off really quick. So we'll stop it there. Thanks everyone for watching. Have a great day.